All right. So hope you were doing well this weekend. I am recording this mini lecture because this is very, very useful material. And I didn't quite have time to cover it in lecture. So you can get along without it. You can do the integrals just fine. But this is going to save you a substantial amount of time, especially on some of the material in this exam and on the next exam. So we're going to look at how to use symmetry to simplify integrals. Essentially, we're going to identify terms in integrands which integrate to 0 without doing any work whatsoever, without actually evaluating any of the integral, which is very, very nice. Very, very nice to be able to do this, and can often save a substantial amount of work. So let's take a look. Okay, so simplifying integrals via symmetry. Whoop. All right. So let's look at functions of 2 variables first. Okay, so a couple definitions. We say a function of 2 variables is x odd if f of negative xy is negative f of xy. So in other words, if you take all the x terms, everything involving x, if you take x and you switch it to negative x in your function, and you move things around or simplify it, you end up getting negative of the original function. So you change x to negative x, you keep y as is, and you get negative of the original function. And we say the function is y odd if you do the same but for y. If you keep x the same, change y to negative y, then you get negative of the original function. So a function of 2 variables can be x odd, y odd, both, or neither. So for example, three x cubed y squared is x odd right? If we change x to negative x, we get 3 times negative x cubed times y squared. And negative x cubed is negative x cubed. We can just pull that out. So we get negative 3x cubed y squared. Right, that's the definition of x odd. You change x to negative x and you get negative the original function, you're x odd. But it's not y odd, right? Because if we change y to negative y, we get 3x cubed negative y quantity squared, which is just y squared. So we get the original function back, not negative the original function. So that is x odd, but not y odd. sine of xy is x odd and y odd, so it's both, right? So for instance, for y, if we change y to negative y, we get sine of x times negative y, which is sine of negative xy. And remember, sine of negative theta is equal to negative sine of theta. So sine of negative something is negative sine of that something. So we get negative sine of xy, which is negative of our original function. Same thing happens for x as well, right? You change x to negative x, you get negative sine xy. So y cos xy is going to be y odd, but not x odd. Right, so you change y to negative y. The negative y out in front, or the y out in front becomes negative y. And then cos of x times negative y is cos of negative xy. And remember, cos of negative something is just cos of something, right? The negative sign doesn't affect it inside. Right, so cos of negative a is equal to cos of a for whatever a is inside. So that cos guy stays the same. The y out in front becomes negative, and you get negative y cos xy when you replace y with negative y. But x, you don't get negative the original function, right? You get exactly the same function again for the same reason. Okay, and so for instance, x over x plus y is going to be neither x odd nor y odd, right? Negative x over, so if we change x to negative x, we don't get negative the original function. We almost do, but on the bottom, we get negative x plus y instead of x plus y. So it's not x odd. Sorry, that's supposed to say not x odd. And then when we do the same for y, we change y to negative y, we don't get negative x over x plus y, which is negative the original function. So we're not y odd either. Okay, so you could be one, the other, both, neither. Okay, so why are we defining these guys, x odd and y odd? Well, it's because of the following theorem. So if we have a function which is x odd, and the region D we're integrating it over is symmetrical in the x direction, about x equals 0. So the region we're integrating it over is symmetrical about x equals 0. So be careful. X equals 0 is the y-axis, not the x-axis. So we're not looking for symmetry about the x-axis. We're looking for symmetry about x equals 0. So symmetry in the x direction. I want to emphasize that. There's a reason I say x equals 0. Yeah. So if the region we're integrating is symmetrical about x equals 0, then the integral over d of our function is 0. So if your function is x odd and the region you're integrating over is symmetrical in the x direction about x equals 0, then your integral is 0. No integration necessary. You can just eyeball it and say that integral is 0. Very easy. But both of those need to be true. Otherwise, you can't say anything about the integral. So x odd, symmetrical about x equals 0 in the x direction. Then your integral is 0 for your function. So the same is true for y, right? So if your function is y odd, and d is symmetrical about y equals 0, oops. So symmetrical in the y direction. Then your integral is 0. Okay. So if either one of these is true, your integral is 0. X odd symmetrical in the x direction, then your integral is 0. Y odd symmetrical in the y direction, integral is 0. Both can be true also. Either one is good enough for the integral to be 0. So let's look at some examples. Let me say first also, often we're going to be using this for things that we would like convert to polar. So let me say what you want to do is you want to check for symmetry. And check your function for x odd or y odd, oddness. And let me say, do that before converting to polar. Oops. Because after you convert to polar, you can no longer, it's no longer obvious looking at the function what you can simplify. Right, so when I say simplify, I mean cancel out the term because it integrates to 0. So do all of this before you convert to polar or get bounds or anything like that. So for example, suppose this is our D. right? So it's the right half of the disk, x squared plus y squared less than or equal to 1. So it's a bit where x is positive. Okay, so first thing you always want to do is look at your region of integration before you look at your integral and check for symmetries, right? So this is symmetrical in the x direction. So it's symmetrical, sorry, in the y direction. So we're symmetrical about y equals 0, right? It's supposed to be a mirror image above and below y equals 0. So in the y direction. So it's symmetrical in the y direction. But not in the x direction, right? Not a mirror image to the left and right of x equals 0. So since it's symmetrical about y equals 0, any terms in our function which are y odd will integrate to 0. But any terms which are x odd, we just have to integrate. Let me say only x odd. You can be x odd and y odd. But if you're only x odd, then you must integrate that term. And let me also say we do this term by term, right? We'll see. Okay. So suppose we want to integrate over this region D. The following integrand. Okay, so we're going to simplify this by picking out terms which we know integrate to 0. Okay, so remember, if you have the integral of one function, so if you have, if the thing you're integrating is a function plus a function, that's just the integral of the first plus the integral of the second. Right, so this is integral over d of the first guy plus integral over d of the second guy plus integral over d of the third guy. And so for each of these terms, right, if we know it integrates to 0, then we can just get rid of it and not worry about it. Okay, so we know because we're symmetrical about y equals 0 in the y direction, let's find all our y odd terms. All of those are going to go to 0. So this guy integrates to 0 because it's y odd. This guy is x, the second guy is x odd, but that doesn't help us here because the region we're integrating over is not symmetrical about x equals 0. So we can't say that integral 0. And it's not y odd, so we can't get rid of it, right? And then the third term, sine of xy, is x odd, which doesn't help us, but it's also y odd. So that integrates to 0 because it's y odd. So we've simplified our integral to the integral over d of just the middle term, xy squared. Okay, so remember I said, so this guy, we would normally convert to polar to integrate it because we're integrating over something bounded by a circle. But if you convert the functions to polar, you can no longer see the symmetries very easily. So make sure you simplify your integral before you convert to polar. Yeah. So then this guy we'd convert to polar. This is just a side note, but we'd say, okay, theta goes from negative pi over 2 to pi over 2. R goes from 0 to 1. And then xy squared would become, so r cos theta, r squared sine squared theta. So cos theta, sine squared theta, whatever. Not important, not important. Let me just say, we would convert to polar and evaluate at that point. We've simplified our function. We've made our life a lot easier. Okay. So let me say, so for functions of two variables, to simplify, let's say double integrals. So the first step is we're going to check our region of integration. For symmetry in the x direction, about x equals 0, and symmetry in the y direction. And then the next step is we go to our integrand. So if d is symmetrical in the x direction, so about x equals 0, then we're going to kill off any x odd terms in the integrand of our integral. Right, so if f of xy has like multiple terms in it, let me just write it like this, actually. Kill off any x odd terms in the integrand. So similarly, if d is symmetrical about y equals 0, then we're going to kill off any y odd terms. In our integrand. So check for symmetry. If we're symmetrical in the x direction, go to your integrand, the thing you're integrating. Any x odd terms are going to integrate to 0. Get rid of them. If we're symmetrical about y equals 0, any y odd terms in our integrand, which are any y odd terms are going to integrate to 0, so kill those off also. And then whatever you're left with find the bounds, convert to polar if you need to, and integrate. You've simplified your integral. So then you just evaluate your simplified integral. Yeah, let me say that. Evaluate simplified integral. So before you do find any bounds for your region of integration, or you change coordinates, you want to simplify your integral. Or if you killed everything off, then your integral is just 0. Okay. So that's functions of 2 variables. Functions of 3 variables, pretty much the same. But now we can be x odd, y odd, or z odd. And we can also, the region of integration in R3 can be symmetrical about x equals 0, y equals 0, or z equals 0. Okay, so the definition is exactly the same. So we're x odd. If you change x to negative x, leave everything else the same. And you get negative the original function. So y odd, if you change y to negative y, leave everything else the same, get negative the original function. And z odd, you can probably guess, change z to negative z. Oops. And you get negative the original function. Okay. So we have x odd, y odd, and z odd now for functions of 3 variables. And similarly, we're integrating over a 3-dimensional solid region. So now we have 3 directions in which to be symmetrical. So let's do an example. So suppose our region W is the region inside. So the solid sphere, x squared plus y squared plus z squared less than or equal to 1. So it's region inside the sphere, x squared plus y squared plus z squared equals 1. But suppose we're taking the upper half of this. So it's the upper hemisphere. I'm going to attempt to draw this. It's not going to be pretty, but bear with me. So that is my beautiful upper hemisphere. Okay, so let's check the symmetries. So sorry, I didn't write down the theorem, but the theorem is exactly the same. So if you're integrating over W and w is symmetrical about x equals 0, and your function is x odd, then it integrates to 0. Same thing, y equals 0, y odd, integral 0, symmetrical about z equals 0, z odd, integral 0. Okay, so symmetrical in the x direction. So x equals 0, remember, is the yz plane. So is this region W a mirror image in front and behind y equals 0 in the x direction? It is. So we're symmetrical about x equals 0 in the x direction. Symmetrical about y equals 0 to the left and the right of y equals 0, the xz plane. It is indeed. Symmetrical about z equals 0. It's not. Right? It's not. You don't have a mirror image above and below the xy plane, z equals 0. So no symmetry in the z direction. So because it's symmetrical about x equals 0, any x odd terms are going to integrate to 0. Same, because it's symmetrical about y equals 0, any y odd terms are going to integrate to 0. And but because it's not z odd, if it's just z odd, we must evaluate that term. If it's x odd or y odd or both, it's going to 0. But if it's only z odd, can't say anything. And if it's neither x odd, y odd, nor z odd, of course, we can't say anything either. Okay. So suppose we integrate over w. And same thing here. Simplify your integral before you switch. Obviously, we would want to use spherical coordinates here. But before you switch to spherical, simplify your integral because you're not going to be able to tell. Find the symmetries and simplify if you switch to spherical. Okay. So suppose we're integrating z squared sine x plus x squared y over z you know what, let me just say x squared yz because that one's actually probably not going to actually integrate. Plus z over x squared plus y squared plus z squared. Suppose this is our integral. Okay. So we've looked at our region of integration, and we've seen that we're symmetrical about x equals 0 and y equals 0. So we're going to find any x odd terms and any y odd terms and kill them off because they're going to integrate to 0. Can't say anything about any other terms. If you're z odd only or none of those, then you have to evaluate. So z squared sine x, that's x odd, right? You change x to negative x, sine of negative x is negative sine of x. So that is going to integrate to 0 because we're x odd. X squared yz, that is y odd, so we're going to integrate to 0. Notice it's also z odd, but who cares? Y odd's the thing that matters here. If it's either y odd or x odd, could be both, it's going to integrate to 0. Z over x squared plus y squared plus z squared. So you can check. This is indeed z odd, but because we don't have symmetry in the z direction over our region of integration, we can't say anything about this integral. We have to actually evaluate it. And so we've simplified our integral as the integral of z over square root x squared plus y squared plus z squared. And that, of course, we'd convert to spherical. And we've already talked about that. Okay, so that is, like talking about the process took a bit of time, but this is something you can do almost immediately when you're doing these problems. You can check symmetry very quickly of your region of integration, and then you can very quickly find x odd, y odd, or z odd terms, and cancel out the stuff that needs to be canceled out. But remember, you have to have both symmetry in your region of integration and oddness of your term in that direction for that to integrate to 0. If one of those fails, you can't say anything about the integral. You have to actually evaluate it. Okay, one last thing I want to talk about. Oops. So suppose you're just interested in we gave you an integral and we said, tell us the sign of this integral. So we've sort of talked about this here. We know when the integral is 0, if our function is x odd and we're symmetrical in the x direction, or y odd and the region of integration is symmetrical in the y direction, then we know the integral is 0. But what about if it's not 0, how do we know if it's positive or negative? So for example, suppose we have the integral over d of, let's say, I don't know, x squared y cubed. Something like this. And let's look at different regions D and see if we can say something about the sign of the integral. Okay. So suppose we had this region here. Suppose that's our D. Well, notice this guy's symmetrical in the y direction, about y equals 0. And our integrand is y odd. So our integral is 0 over this guy, right? We just talked about that. But suppose, oops, now we had this as our region D of integration. So this is symmetrical in the x direction, but our integrand is not x odd. So we can't say that the integral is 0. And in fact, the integral is not going to be 0. So let's see what we can say about this. Well, notice x squared is always going to be positive, right? No matter where you are, because you square something, it's always greater than or equal to 0. Y cubed is always going to be positive in the upper half plane, right? So where y is positive, y cubed is positive. So our function's positive on this entire region, right? So if it's positive on the entire region, then the integral is going to be positive. Right, so our integral is going to be positive in this case, because it's either 0 or greater than 0 on the entire region of integration here. And how about say this region here? Oops, okay. Suppose this is our region D. Okay. So we're going to do a little trick here. So it's sort of this trapezoid guy, and it goes, whoops, up to y equals 1 and down to y equals -2. And it's wider on the bottom than it is on top. What we're going to do is we're going to sort of carve out a little region where the integral is going to be 0, and then see what we're left with. So notice this. So it's asymmetrical, right? But we can find a region inside of here where the integral is 0 by, well, there are two ways to do this. So we can find a region that's symmetrical in the x direction. Let's do that. So let's find the biggest region inside of here that's symmetrical in the x direction, that lies entirely inside of D. Actually, hang on, that's unfortunate. So notice this region. Oh my goodness. Notice this region in here. We'll call it D bar. Lies entirely inside of D, and it's symmetrical in the, oh, shoot, sorry. Hang on. Okay, we're sorry. Okay, sorry. X odd doesn't help us, right? Because it's not going to integrate to 0 because our function, symmetry in the x direction is not going to help. We need symmetry in the y direction because our function is only y odd. So we're going to find the biggest region inside of here, which is symmetrical about y equals 0. That's going to be this guy here. We'll call that D bar. Notice that lies entirely inside of D. So the integral over D bar of our function, so x squared y cubed, is going to be 0. Oops. Because D bar is symmetrical in the y direction, and our function is y odd. So we'll call the remaining region D prime. So we're left with a region which lies entirely below the y-axis now. So because the integral over that whole thing was 0, the integral over all of d is equal to the integral over d bar, which is 0, plus the integral over d prime. Oh my goodness. Right, because the integral over all that, over d bar, that piece of it is 0. And what is the sign of the integral over d bar? Well, it lies entirely below the y-axis, right? X is always positive and y is always negative in that region. So our integral is negative. Because x squared y cubed is less than or equal to 0 on d prime. Okay, so hope that was helpful. Yeah, don't ignore this last bit. You need to know that. But for this exam and the next exam, simplifying your integrals is going to save you a lot of time because evaluating integrals takes a while. And you can simplify them at a glance using symmetry. And we're often going to give you integrals that can be simplified. And that'll save you substantial amounts of time. So yeah, all right.